In this section, we're going to talk about the table method. We've solved linear programming problems graphically, but that method is only really efficient when we have two decision variables and a relatively small number of constraints. To handle larger systems, a method called the Simplex Method was developed in 1947 by George B. Danzig. It's very computer friendly, and it's routinely applied to linear programming problems involving thousands of variables and problem constraints. But to understand the Simplex method, we're first going to examine the table method. First, we consider this word problem. The Crumb and Custard Bakery makes coffee cakes and Danish in large pans. The main ingredients are flour and sugar. There are 25 pounds of flour and 16 pounds of sugar available each day. 5 pounds of flour and 2 pounds of sugar are required to make a pan of coffee cakes. 5 pounds of flour and 4 pounds of sugar are required to make a pan of Danish. A pan of coffee cakes has a profit of $1, and a pan of Danish has a profit of $5. Determine the number of pans of coffee cakes and Danish to produce each day so that the profit will be maximized. So this is sufficiently small enough that we could solve this graphically, and so we did. So you can see here, we let x equal the pans of coffee cakes and y equal the pans of Danish. So our objective function z that we are to maximize was x plus 5y. The flour constraint is 5x plus 5y is less than or equal to 25. And we graph that in purple. The sugar constraint, 2x plus 4y less than or equal to 16, we graphed in the red line. And then we have our non-negative constraints, x and y greater than or equal to 0, as we will not make a negative number of pans. After we graphed, we found the solution region, and we found the corner points 0, 4, 2, 3, 5, 0, and of course, in this case, 0, 0. We then found that the corner point 0, 4 maximized our problem, and so we found that the bakery should make no pans of coffee cakes and 4 pans of Danish daily to maximize their profit, and that profit would be a maximum of $20. Now, we can apply this problem to the table method. But first, let's talk about a few things. One thing to notice is that the problem constraints involve less than or equal with positive numbers on the right and non-negative decision variables. This is called a standard maximization problem, and in this type of problem, the coefficients of the objective function can be any real number. So technically that means that x and y could have negative or positive coefficients in front of them, and that's the type of problem that we're going to consider for now. In order to adapt the CNC bakery problem to a table method, we have to adapt it to a matrix method. So that means we have to convert the problem constraint variables into a system of linear equations instead of inequalities. To do that, we're going to use what we call slack variables. These are variables that make up the difference between the left and the right side. Essentially, they take up the slack. This new system is going to be called an E system for an equality system. The inequality system is called an I system. So, an example, we're going to convert the CNC bakery I system to an E system. So the flour constraint, which if you recall in the parentheses here, 5x1 plus 5x2 less than or equal to 25. In order to make that an equal statement, we would have to add a certain number to make that equal to 25. So we're going to add S1. That is our slack variable. Now S1 could be 0 or it could be a positive number, but it is always non-negative. We're going to do the same for the sugar constraint. So recall that the Sugar constraint was 2x1 plus 4x2 less than or equal to 16. Well, in order to gain equality, since this was less than or equal to 16, we're going to have to add something to the left side to make it equal to the right. So we add S2 as our slack variable. Now, just like S1, S2 is always non-negative. And S1 and S2 are completely dependent on X1 and S2. And we can see this in the example below. If C and C makes 1 pan of coffee cakes and 3 pans of Danish, what is the amount of flour left over? Well, we can find this out by using the flour constraint. So, 5 times 1 plus 5 times 3 plus S1 equals 25 would give us a value of S1 equals 5. And that means there are 5 pounds of flour left over. Now we're going to look at the procedure for the table method with 2 decision variables and M problem constraints. Now, this does not include the non-negative problem constraints. We're going to look at 4 steps. The first step is converting the I system to an E system by using slack variables S1 through Sm. Step 2 is to form a table. The number of rows is determined by the equation m plus 2 times m plus 1 over 2. The number of columns may be calculated by m plus 2, and the columns will be labeled x1, x2, followed by the slack variables s1 through sm. Now, in the first row, we're going to assign the value 0 to x1 and x2. In the second row, we'll assign 0 to x1 and s1. And we're going to continue until the rows contain all possible combinations of assigning 2 zeros to the variables. Now, this is an important definition. The variables that are assigned the value 0 are called non-basic variables. The non-zero variables are called basic variables. Step 3 is to complete each row to a solution of the E system if possible. Because 2 of the variables are 0, this involves solving a system of m linear equations in m variables. So we can use Gauss-Jordan, substitution, elimination, or other methods. If the system has no solution or infinitely many solutions, we will not complete the row. Step 4, we'll solve the linear programming problem by finding the maximum value of z over those completed rows that have no negative values. Now remember, the columns in the rows are going to represent x1 all the way through the slack variables. Now, x1 and x2 are non-negative, and so are the slack variables. So that's why we're going to throw out any rows that have a negative value, because the x's and the s's should be non-negative. So if we have a row with a negative value, that is considered a non-feasible solution. Otherwise, the solution is feasible. However, we do say that each row yields a basic solution. We just have to determine if it is feasible or not feasible. So now we're going to solve the CNC bakery problem with the table method. First, the number of constraints in this problem is 2, flour and sugar, so m equals 2. The number of rows needed we can calculate as m plus 1 times m plus 2 over 2, and that gives us 6. The number of columns needed is m plus 2, which is 4. So we can see here we have x1, x2, s1, and s2. So basically the way we build our table is we take the zeros and we put them with x1 and x2, and then we put a 0 with x1 and s1, and then with x1 and s2. So now we've paired x1 with every other variable there is. So now we move to x2. Well, we've already looked at when x2 and x1 are 0, so now we consider when x2 and s1 are 0. And then in row 5, x2 is 0, s2 is 0, and in the last row, the slack variables s1 and s2 are both 0. So we've listed every possible pair of zeros among the element. Now we are going to complete the rows and continue to solve the problem, but for now let's talk about the difference between the basic and non-basic variables. So remember the definition. The basic variables have a non-zero value. The variables that have a 0 value are non-basic. So in row 1, x1 and x2 have a 0 value, so they are non-basic, while s1 and s2 are the basic variables. In row 2, the non-basic are x1 and s1 because they were assigned the value 0. So the basic variables are x2 and s2, and so on. On the next couple of slides, I've just shown how we solve the rows. We're using substitution in some of these, in some we're using elimination. I'm not going to talk through each of these. I'll just talk through a couple of them. Feel free to pause the video if you'd like to look at the solutions. But I put our e-system on the top, 5x1 plus 5x2 plus s1 equals 25. 2x1 plus 4x2 plus s2 equals 16. And for example, I'm just going to talk through row 3. So in row 3, we had let x1 equal 0 and s2 equal 0. So I'm looking at this last box here. So I plug in 0 for x1 into my first equation, and that gives me 5 times 0 plus 5x2 plus s1 is 25. So I have my arrow pointing to 5x2 plus s1 is 25. And that is the most I can do with that particular equation for now. So let's look at our next equation. I know that x1 is 0 and s2 is 0. So I'm going to substitute 0 in for both of those. So 2 times 0 plus 4x2 plus 0 is 16 yields 4x2 equals 16, which gives me that x2 equals 4. So I now know the value of the basic variable x2. So I can take x2 and I can plug it into 5x2 plus s1 equals 25, and I can now find the value of s1. So I have 5 times 4 plus s1 equals 25, so s1 equals 5. And the next slide continues this for row 4, row 5, and row 6. Now the computation in row 6 is actually an elimination. This is actually the same computation we did in the graphical method to find the corner point 2, 3, as it was the intersection of the two lines. So this is our completed table. So we see that in row 1, when x1 and x2 are 0, s1 and s2 are 25 and 16. Now, if you recall the original problem, this makes sense because we started with 25 pounds of flour and 16 pounds of sugar. So x1 represents the pans of coffee cakes, and x2 represents the pans of Danish. So this makes sense because we've made no pans of coffee cakes and no pans of Danish, so we've used no flour and no sugar yet, so we have the full amount. And so you can continue to look through the table and you can see in row 2 our variables x1 and x2 are 0 and 5, slack variables 0 and -4, and so on. To the side, I've added an additional table that will help us answer two questions. Does this row contain a feasible solution? And if so, what is the value of our objective function z equals x1 plus 5x2? Remember, our goal is to solve the crumb and custard bakery problem, and this was our objective. Now note, since x1, x2, s1, and s2 have to be greater than or equal to 0, any row containing a negative number is not feasible. So because the first row does not contain a negative number, it is a feasible solution. So if I were to plug x1 and x2 into z, I get 0. In row 2, I have a negative value for the slack variable s2. So I have no feasible solution. In row 3, all of my variables have a value of 0 or positive. So that is a feasible solution. So I will now substitute 0 in for x1 and 4 in for x2. And so I get 0 plus 4 times 5, which is equal to 20. Row 4, I have no negative numbers, so that is also a feasible solution. So I will plug 5 and 0 in to z, and I will get 5. My next row is not feasible because s1 has a negative 15 as its value. The last row is a feasible solution, so I use 2 and 3. I input them into z, and I get 18. So the solution that maximizes z is x1 equals 0 and x2 equals 4. This matches the answers we found using the graphical method. Another thing that we should note is that all of the feasible solutions in the table are actually the corner points we found in the graphical method: 0, 0, 5, 0, 0, 4, and 2, 3. So all of the feasible solutions are matching to the corner points. Note also that in row 1, once again, x1 and x2, because they are 0, are considered non-basic variables. s1 and s2 are basic variables because they have a non-zero value. In row 2, the non-basic variables are x1 and s1, and we found x2 and s2 to have non-zero values, just as expected, so those are basic variables. So we have efficiently solved the crumb and custard bakery problem both graphically and using the table method.